optimization problems. In this section, I will solve a couple of problems involving maximization or minimization factors. In order to solve optimization problems, we have to something depends on the scenario. That means, for example, we may maximize an area, volume, profit, of course, or minimizing distance, time, cost. We do have some steps, some guidelines, how to approach the optimization problems. Optimization problems are theoretically the word problems involving, of course, calculus. First of all, we have to read and understand the problem, draw a diagram, if you can, of course, introduce the notation, variables, state the given information and the required information. It's important to notice what is given, what is required, and then determine if we're maximizing or minimizing in the particular problem. Because not always the word maximizing or minimizing will be stated explicitly. We have to always read exactly the question. Then, if we realize what we have to do, we have to find a function in terms of one variable, that we have to find all of the additional relationship, rewrite one variable in terms of the other, and create a function. Then domain of the function is important because we have to find the absolute maximum or absolute minimum. That means domain is critical. And of course, the critical points are the important factors of the equation, because not always, but most likely the extreme values, they happen at critical points. And then always make sure that you answer the question. Okay, that means let's solve a few problems. Example number 1. An open rectangular box with square base is to made from 48 square feet of material. What dimensions will result in a box with the largest possible volume? That we can see. We have a box. We know what is the surface area because we can build the box with the 48 square feet material. That we have this given. And the question asks for the maximum volume. And we can see the largest possible volume, which is not stated explicitly, but we can definitely read from the word, descriptive word largest, that we're looking for the maximum. That means the given information is the surface area, 48 square feet. We also know the formula. If I label the box, it's the square base and the height. Okay? That means the surface area of the open box is the base, x squared, and 4 times xh, the size. Required information is the maximum volume. Of course, we also know the formula for the volume, length times width times height, x times h, x squared times h. And as we just saw in the guidelines, that we have to find the function in terms of one variable. That means the given information will help me to get the relation between h and x, and I will rewrite h in terms of x and substitute to the volume. X squared plus 4xh is equal to 48. Then solving this equation for h, I'm getting this. And this equation, this relation, will travel here. And then I have a function in terms of one variable x, and this is my function that I have to maximize. First of all, let's simplify a little bit. I cancel out one of the x squared and x. And then I can probably multiply 48 times x, and x squared times x is x cubed, and also divide by 4. 48 divided by 4 is 12, and x squared divided by 4 will stay 1/4. That means I have nice expanded form. I don't have to really think that I have to use past the quotient rule, I have just two terms. Of course, I'm thinking in terms of the derivative for the critical points. Okay, that's me having this function. In order to maximize, I will find the derivative for the critical points. But before I will do this, I will just state the domain. And the domain usually is like restricted by the given information. That we can see we can't have a certain numbers of x and h because of that 48. And we can see nicely here. That means h is defined as a 48 minus x squared. Since this is the length, 48 minus x squared must be positive. We can't have a negative values. That means solving this, I can see that x can be only chosen from between 0 and square root of 48. And since this is open interval, we will not look at the values at the endpoints, which actually they will give me 0. That means we have to find the critical point, test it for maximum or minimum, and then get the answer. Okay, let's differentiate. That's what we're trying to do. That's the volume. Derivative of 12x is 12. Derivative of 1/4 x cubed is 3x squared over 4. Derivative is 0 if the whole expression is 0. And I can solve this expression for x. Subtracting 12 and multiplying by -1, cross multiplying will give me x squared equals to 16. That's when we have 4 and -4, but of course -4, we're not accepting negative. And then I will do the test. Okay, this is 4, this is my derivative, and I can maybe pick 1, and this is good form of the derivative. If I will put 1, I have positive number, and if I will put huge positive number as a testing point, I will have minus negative. That means function is increasing and decreasing. At 4, at x equals to 4, function attains maximum. And it's local maximum. As I said, we don't even have to substitute 0 and 48 because that's not really the endpoints because the interval is open. If I am looking for the absolute maximum using extreme values theorem, that means I took the formula for the volume, which is here, and substituted 4. That means 32 represents the maximum volume. But however, let's check what the question was, find the dimension. That means this will be x and x, length times width, and height. I can compute height because height was given as a 48 minus x squared over 4x. That means 48. And x is 4, 16, 4 times 4, 16. 32 divided by 16 is actually 2. That means h is 2 with x being 4. That means they not, sometimes the question asks for the maximum volume in this case, but in this case, the 32 was not even required, the dimension, 4 by 4 by 2. And that's definitely maximum. Remember about the test, first derivative test. Okay, that means that's what we will do. Let's look at example number 2. A cylindrical can is to hold 20 pi cubic meters. That means this is volume. The material for the top and the bottom cost $10 per square meter, and the material for the side costs $8 per square meter. Find the radius and height of the most economical can. Again, for the most economical can, that means we have to minimize the cost of the material. Minimizing the cost of the material, I have to minimize the surface area. I have to make it as small as possible with that volume, 20 pi. Okay, that means the given information is volume. And I know that the formula for the volume is the area of the base, pi r squared times h. Okay, excellent. And the required information is costs. We have to minimize the cost. First of all, I will start with the surface area. That means let's see how this cylindrical can is built. We do have two bases, the bottom and the top, and they are the same. And this is just pi r squared times 2. And if I will cut the top and the bottom bases, we will just get cylindrical shell. Yeah, like you can probably imagine a soda can without the top and without the bottom. It's just the shell. I can take that shell and cut in the line perpendicular to the base. That means I can cut and put it flat, and you can probably picture this. We will get a rectangle. The area of the rectangle is length times width. The length of this rectangle will be simply something that I can create a circle, a circumference. That means this will be 2 pi r and times width, which is h. Okay? That means 2 pi r and h. And we can see two bases, top and the bottom, and the rectangular side. Okay, now this is the surface area, but I still have to create a function that represents the cost, which means if this is amount, 2 pi r squared, that's the amount of the material that I need for the bases. That means, let's say is, I don't know, 2 meters square, 5 meters square, 10 meters square. In order to buy the material, I have to multiply by 10 because it's $10 per 1 meter square. That means that amount I am multiplying by $10. And this is the amount of the site, which costs only 8. I mean, cost 8. And I'm multiplying that amount of material by 8. Okay, let's simplify a little bit. I was gonna multiply everything, but again, the same situation. We will minimize a cost function. However, I have to have a function in terms of one variable. At the moment, I see radius r and height h. I will rewrite the given information in terms of one variable in terms of the other one. That means it looks like that if v is 20 pi, I can nicely solve this equation for h. That means pi r squared times h equals 20 pi, dividing by pi, of course, and solving for h, I have 20 over r squared. That means this is the relation for h in terms of r, and this will travel to that. And then the c, the cost function, will be defined in terms of one variable. I copy this. 8 times 2 is 16 pi r, and that's h, 20 over r squared. And this one, we can see we don't really have restriction because r could be any positive number. That means just positive numbers. H and r are positive. That means we have to find a critical point and test for local extreme value. Okay, 16 times 20 is 320 pi, and r squared, 1 is gone. Okay, let's differentiate. That's the cost function. Derivative is 20 pi, and derivative of r squared is 2r. I multiply 2 times 20, 40 pi r. And then 320 pi, it's a constant. Derivative of 1 over r is negative over r squared. Let's get a common denominator, multiplying this by r squared, getting r cubed, and derivative is 0 if this formula is 0. Fraction is 0 if the top is 0, never denominator. Factoring out common factor, 40 pi, and leaving us in the parentheses with r cubed minus 8, and of course r is 2. That means let's test this. If the radius is 2, let's see what's happened with the derivative. I can take, this is nice formula of the derivative. If I will put 1, I have negative. If I will put like 10, it will be positive value. Then the cost function is in decreasing and increasing. That means we do have local minimum value at 2. Cost will be minimum at radius 2. And now I believe they ask for, let me come back. they find the radius and the height. We always have to double check what they ask for. That means radius is 2. And now we can compute height. And height, I believe height was, I don't remember, 20 over r squared. That means height is 20 over r squared, which height will be 20 over 4, 5. That's the final answer. Radius is 2 and the height is 5. That we can see it's not, it's quite, the radius is quite tall, I would say, taller than like wider. Okay? And this will give me a minimum amount of the material built, because F2 is the minimum value of the cost function, which cost function includes the surface area. Okay, now example number 3. Find the point on the line y equals to 4x plus 7 that is closest to the origin. Okay, that means the only information that is given is the equation of the line, and the origin means 0.00. That means the given information is just the line, and the required information is the closest to the origin, which means the distance. We have to create a function that represents the distance between the line and the origin, and this distance must be minimum. So what we can do, and what we can also do before I start inputting the values, like it doesn't really matter if I will minimize the distance or distance squared. That's the same thing. Minimizing, we can see minimizing the quantity inside will minimize the entire distance. That means let's just name the function d squared and minimize this. Thinking in terms of the derivative, we can simplify a little bit. Okay, that means what I will do, I don't have the graph, but I can possibly graph a function. Y-intercept is 7 and x-intercept will be negative 7 over 4. That means we're looking for the point. This is origin, 0, 0, and we're looking for the point somewhere here. Of course, we're not gonna guess. That means what I have. I have x minus 0, y minus 0. X minus 0, y minus 0. That's the points. And I also know that I have to rewrite my function in terms of one variable. That means I have x and y at the moment. I will replace y with the given formula for x plus 7. Okay. Really nice function, just in terms of x. Let's find a critical points. Okay, I did expand the function. We don't have to expand because we may find the derivative using the chain rule. But I did expand, it's still fine. Now I have expanded form, I can differentiate term by term. The chain rule will be avoided. Okay. Oh, actually my derivative is on this side. It's okay, I can draw this picture one more time. That means derivative will be 34x plus 56. And derivative is 0 if x is negative 56 over 34, dividing by 2, negative 28 over 17. And the y value, hang on, let me actually draw, because we have to do a few things. I will still draw the line, 7, negative 7 over 4, and we're looking for the point. The closest point to the origin will be here, x, y. And we just got the answer that this will be negative 28 over 17. I think looks good because 7 over 4 is more than 1, and 28 over 17 is, it's less, I mean, I believe this is less than this one. Yeah, am I right? Because we can theoretically find a common denominator, but this is definitely 17 times 2 is 34. That means this is definitely less than 7 over 4, because 7 over 4 is almost 2. That means this one is definitely bigger. Okay, and we can find the corresponding y, but the only thing is we have to double check if this number, negative 28 over 17, for my derivative, is giving me, I mean the first derivative test is showing me that this is a minimum value for the function, for the d squared at that point. That means what I can do, I can pick maybe negative 2, and where is my derivative? This is good derivative. That means if I put negative 2, I will have negative number, and if I will put 0, I will have positive. That means d squared, my distance, is decreasing, increasing. That means it is local minimum, but it's also absolute minimum because we don't have any other lowest point. That means this is the lowest. That's the extreme value, the extreme minimum, and this will give me the closest distance. And I was trying to compute y value. You can simply do the arithmetic. Negative 4 times 28 divided by 17 plus 7. I will just leave it like that. Okay, but that's the x and the y value. That's the point. And that we can see we did minimize a distance. Okay, let's solve one more question. And okay, I don't have the solution for this one, but I can write it for you. Okay, example number 4. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Okay, that means this one is telling me almost explicitly that we have to maximize an area. Okay, that's what is given. Given information is 2,400 feet, but since this is fence, I can say parameter. Okay, and I can draw, this is a river, and he needs a fence here, here, and here. And I can say possibly x, y, and y, or the other way. This is definitely, it must be equal. I mean, my labels are telling us that it's equal. Y and y. Okay, that means that's the parameter, but we have to be careful. The parameter is only x plus 2y. X plus 2y. That means x plus 2y equals to 2,400. And I can solve this equation for x. This will be 2,400 minus 2y, because we just learned that we will need one variable in terms of the other to get the function of one variable for maximization. Okay, that means that's the given information. The required information is an area, maximizing the area, the largest area. That means the area is just length times width, x times y. And since this is x and y, I need just in terms of y, let's say. That means I will keep y and x equals to 2,400 minus 2y. Let's distribute 2,400y minus 2y squared. Really nice function. We do have some restriction actually, because the given information 2,400 feet is giving me restriction. That means 2,400 minus 2y must be positive. That means 2y must be less than, y must be less than 1,200. That means this is the main. But it's open interval. In order to find the absolute maximum, we have to find a critical point. That means let's differentiate. Derivative will be 2,400 minus 4y. And the derivative is 0 if 2,400 minus 4y is 0. That means y is, I believe, 600. It's less than 1,200, works. But let's check if this is y 600. Let's check the sign. I can put maybe 0, I will have positive, and if I will put bigger number than 600, this will be negative. That means the area behaves like that, increasing, decreasing, and it is maximum. That means when y is 600 function, the area attains maximum. And we have to find not the maximum area, x times y, we have to find just the dimension. That means dimensions are 600 by, and we have to compute x. X is this. That means 2 times 600 is 1200. 24 minus 1200 is actually 1200. Okay, that means is the y is 600 and the x is 1200. Okay? That's the dimension of the largest area. And I also have a picture. Yes, we can see, because we don't know how to distribute this 2400, 100, 100, and 22, 10, 10, and 4, 7, 7, and 10. Yes, we don't know how to, we have to maximize the area. That means that's what I did. I did the other way, the labels, but that's how we can deal with the x and y and the possible larger. Okay, that's mean what you can do. I do have few more problems on this, but you can definitely try to practice even the same problems. I did solve 4 problems for you. If you have other problems, please put on the discussion board and I will definitely assist you. Okay? Good luck with your assignments in this week. Thank you.